Hey, physics kids, Mr. Johansson here. We're doing the spring lab. So we're going to be taking this setup here, which has a scale measured in centimeters, and we have a mass hanger here, and the actual spring is right here. And we're going to be testing the spring, coming up with the spring constant, how much energy is stored on it, seeing if the spring constant is really constant, stuff like that. I'll give you a lot of data, or some of the data, and you have to figure out the rest. I'll show you how to do it on the data table. Right now, I'm going to take the data from this. So one of the things that I need to mention before we go forward, look at a spring like this. Now the spring constant is a pretty perfect constant, but you'll notice if I hang little tiny weights on this, it won't even do anything. Does that mean it doesn't work? The spring constant is not real? Well, no. The deal is that unless you start to displace a spring, as long as the spring has started to stretch out, now it'll obey the spring constant. But some springs are so tough that you hang a little mass on it, it's not going to have any effect on it at all. So you have to get over that first. You have to get the spring to begin to stretch. Now, on this device, this little hanger has some weight on it, and it makes the spring, because these are very gentle springs, it makes them begin to stretch. So then when I hang these masses on it, the spring has already begun to stretch, so then it should give us very, very good spring constant readings. So I'm going to hang 50-gram masses on it, one after another, to a total of 5. And as I hang each one, I have adjusted this so it's at 0, and I will give you the displacement that it undergoes with each mass on it. So you can follow along and do this lab at home. Or if you missed it in class, you can do it again. All right, so the first mass goes on it, and it stretches to 2.2 centimeters with 50 grams of mass on it. The second mass, so now it's 100 grams of mass on it, stretches to approximately 4.5 centimeters. Okay. The third, so now it's going to be 150 grams on it. It stretches down to about 6.8 centimeters. Another one, so now it's going to be 200 grams hanging on it. And that looks to be 9.1 centimeters. And the last one, so now it's 250 grams on it. And approximately 11.4 centimeters. So that's it. That's all the data gathering we need here. So we'll take these back off so we don't leave the spring all stretching. And so we're going to want to take this data and fill in our data table. So come on up here and let's look at the data table. Now, when you're doing labs, having a good data table saves the day. It's a really important understanding. Make your data table so everything you need, you have a place to put that data in, so you could do your experiment, get all the data you need, and then you could do all the calculations and fill in the rest of it. So let's take a look at this data table, shall we? All right, so filling in the data. Trial number 1 here, let's look at this. Trial number 1, the mass was 50 grams. That's what it says on this. I don't want to have to do any calculations. I might get them wrong. I want to see exactly what the raw data was. So make sure on your data table you have a place to put the raw data, calculate it later. But you can always go back to the raw data if you have trouble and ensure that that was captured correctly. So we have 50 grams. Well, what do I multiply to change it into kilograms? Everybody who said 1, congratulations, good job. You multiply it by a form of 1. I'll let you figure out what form of 1. We've done that a few hundred times. In any case, this comes out to 0.05 0, that's significant, kilograms. What is the weight of a 0.050 kilogram mass? How do you determine weight from mass? Okay, well, you multiply it by 9.8 meters per second squared. So if I multiply this, well, if I multiply it by 10, it would be 0.5. So you know it's going to be a little less than 0.5. This comes out to 0.49 newtons, kilogram meters per second squared. In Earth gravity, that's how much weight I was actually hanging off the spring. Well, what's the stretch? I had given the stretch as 2.2 centimeters, right? So this is exactly where I would fill that in, right here. Okay? Well, what is that in meters? Okay, what do you multiply? You multiply by 1 and 0.022 meters. Then you calculate the spring constant. Okay, the spring constant is going to be newtons per meter. There's your newtons, you divide by your meters there, that'll give you your spring constant. Should the spring constant be approximately the same number all the way down? Well, is it the same spring that we used all through the experiment? It is. So should the spring constant vary? The word constant implies no. We don't want the spring constant to vary. So if we measure it really well and do a good job with all of that, the spring constant should come out pretty close to the same all the way through. And then the last one is how much potential energy is stored in it. And that equals 1/2 kx squared. So you have all that data. Should this change? Well, you do the calculations and see how that changes. I'll let you do the calculations for K and PE yourself. It's kind of the lab. But let me give you the rest of the raw data on the data table for you. Okay, and the next mass for trial number 2 would be now 100 grams, then 150 grams, 200 grams, and 250 grams. Okay, the stretch in each of these cases is 4.5 centimeters here for trial number 2 with 100 grams on it. With 150 grams on it, it came to 6.8 centimeters. With 200 grams on it, it came to 9.1 centimeters. And with 250 grams, it came to 11.4 centimeters. Everything else, you figure out. It's a lab, all right? So do this, put it all on the lab sheet that I have a PDF on file for, and submit it. You've done a lab, the spring constant lab. It's pretty cool. Springs are everywhere, and understanding them a little bit better, you're going to use springs your whole life. Thank you. Bye-bye.